Hello, everyone, and welcome to another wonderful day of statistical mechanics. So over the last couple lectures, we are able to build up a set of molecular partition functions. So today what we're going to do is try and put these molecular partition functions to use in describing the energy of a system. So when we're trying to figure out the energy of a system, a good place to start is trying to come up with the average energy of any given molecule. Now, this should actually be fairly easy to start with this idea that the average energy per molecule can simply be the total energy divided by the number of molecules. Well, we can go ahead and just pull out 1 over n here, but because we already described the total energy of the system as essentially the sum of over all states of the energy of each individual state times the number of molecules in each state. So from here, we can go ahead and make use of several of our features in describing the number of molecules in any given state. So we already described this as equaling essentially the Boltzmann distribution. And one of the important things when we describe the Boltzmann distribution is we had it as Ni over n. So the n here, Ni over n will disappear, replaced instead by the probability of each state, so more or less the weight of each state, so the exponential of E over K, energy of each state over KT, again, over the partition function. So one of the easiest places to start when trying to describe this is that the partition function will not depend upon the state that we're examining. So I can go ahead and pull the partition function out in front of our expression, and what I leave behind is a sum over the energy of each state times essentially the weight or probability of each state, the exponential of E over KT, negative E over KT. So from here, a good way to try and treat this system is how to look at E over KT. Well, it turns out this energy times e to the negative beta kt would be the same thing as the exponential part of this function, the derivative of the exponential part of this function with respect to beta. Because if I take the derivative with respect to beta, what pops out is just negative negative of the energy of the state. That pops out front, negatives cancel. I get energy of the state, exponential negative E beta. So one of the ways to try and describe our system is going to be replacing this sum term with respect to the derivative of our exponential portion of the expression. And this is a good way to essentially eliminate the energy of each state from the precursor, which will be very useful later. Now, in terms of analyzing kind of the meaning of this expression, one of the important things to remember is that what we're talking about when we're talking about beta. So our beta is, again, our Boltzmann constant, but more importantly, it's also an expression of temperature. So to a certain degree, what I'm looking at when I'm taking the derivative of this exponential of the energy with respect to beta is I'm really taking the derivative of this energy or probability portion of my function with respect to temperature. I'm to a certain extent looking at the temperature dependence of my probability function. So what we're going to do is making use of replacing my energy times the exponential with this derivative function, I can go ahead and clean up my sum expression here a little bit. So what I can first do is say, well, I've got 1 over q times the sum of the derivative of this exponential function. But you'll notice this derivative has no dependence on what state I'm in. So I can actually pull it in front of the derivative. Now, here I've now finally simplified myself to the sum of the exponential of negative beta over EI. Well, this is our exact definition of the partition function. So what I've generated is negative 1 over q, the derivative of the partition function with respect to beta, which is, again, another useful way of looking at it with respect to temperature. So the final expression is, hey, wait a minute. 1 over x, derivative of x, is the same as the derivative of ln of x. So we can replace this 1 over q dq expression with the derivative of the natural log. This is an expression we've used occasionally to help clean up some of our math. And as you've noticed, we've actually, through the virtue of several messy steps, been able to actually simplify this expression. There's no nasty sums, nothing complicated. As long as I have an expression of my molecular partition function, which we've already come up with ways to describe our molecular partition function of the system often without sums, I can go ahead and get the average energy of a molecule. However, here we have to watch out with one last remaining nuance. And all of our energies that all of our partition functions we derived so far were always with respect to the ground states of energy of the system. And it's important to note that the ground state energy of a system isn't always zero. So in truth, we actually have to modify the ground state energy of the energy of our system with respect to the ground state. So we have to essentially add on this extra term on top of whatever the ground state component was already determined to be. And this often has to be determined experimentally, but in truth is often held as quite arbitrary. And so unless you have an explicit reason to go after it, it often tends to be a little ignored. But one of the other important things should also make note of is when we incorporated our derivative into our energy expression, we also applied this extra constraint here. We're trying to hold essentially volume constant. And one of the reasons why we're trying to do this is volume is kind of the only variable that was kind of left to vary. So essentially what we're doing is we're holding all other variables besides temperature constant. So when we're looking at the energy of the system, we're essentially holding volume constant because by virtue that also helps us hold pressure fairly constant. And again, the only variable that's then allowed to vary is temperature. So this gives us a general way of tackling the energy of the system. All I need to do is determine the energy of the ground state and try and figure out how the natural log of my partition function varies with beta. I do that and I'm golden. However, as you've noticed, we have several different expressions for our molecular partition function, and it often just depends on what type of movement we're handling. So of course, the simplest of which to handle is going to be the electronic partition function. Since the electronic partition function is just one, the average energy for the electronic component is 0. So all of the electronic energy is essentially held in the ground state energy, and we don't have to worry about any statistical mechanical contributions to the electronic energy. The other three can be a little bit tricky. So let's go ahead and start with our good old friend, the translational partition function. So here, what we're going to do is similar to what we've done before. We're going to start by focusing in on the average energy just with respect to movement in the x direction. That way, the only partition function I have to examine is the partition function with respect to x. So we can then go ahead and input our translational partition function. Here, I went ahead and replaced our 2 pi mass kt with 2 pi m over beta, because again, kt is the same as 1 over beta, and then again times x. So what we can do here is then try and figure out if I'm taking the derivative of this whole component with respect to beta, is there any way to just isolate the beta terms? Well, since I've got a natural log, I can treat this beta as -1/2 and just remove it out. So the derivative of natural log of beta to the -1/2, leaving behind derivative of natural log of, wait a minute, this is a whole bunch of constants because I don't see a single term that's dependent upon the temperature here. So this whole former expression is just a whole bunch of constants, so it goes to 0. And all I'm left with is negative of the derivative of the natural log of the negative square root of beta. Now this seems a bit messy, but by doing a simple derivative, we're actually able to just pop out 1 over 2 beta. because essentially by pulling the derivative of the natural log, it ends up just being the derivative of the inner component, and and the negatives end up canceling out, and all we're left with is 1 over 2 beta, which again is often then expanded by replacing the beta into kT of 1/2 kT. Now, if you remember way back to the beginning of the class, I said that every degree of freedom, essentially every degree of translational motion, had 1/2 kT of energy. Here's where it comes from. So if I have if I have movement in all three directions, x, y, and z, I can then just add these three components together, and my total translational energy is 3/2 kT. Again, per molecule. So on a molar basis, for the whole system, this gives us a total energy of 3/2 nRT. So if you wondered where this mysterious 3/2 nRT comes from, it turns out it comes from statistical mechanics. So we can actually, through this, help confirm many of our suppositions that we've been using throughout the semester of ideal gas behavior. Because again, an atomic ideal gas only has translational motion. If it's just an atom, there is no rotational vibrational character. However, if it's a diatomic, I have to start worrying about rotational behavior. So we're going to go ahead and start by trying to examine the rotational behavior of again, we're going to start with a linear molecule. So this will help keep our partition function fairly simple. In addition, we're also benefited by the fact that rotational movement has no ground state energy. So I'm able to provide the average energy for the system as just -1 over q dq d beta. So what we can then do is use our expression for the high temperature partition function. And again, it is worth noting when I'm talking about high temperature, it pretty much just means room temperature qualifies as high temperature for rotational motion. Though it is worth again remembering that this would break down if I go to significantly cool temperatures. But under room temperature, I can treat the rotational partition function as the temperature over the rotational constant, which again can then be the characteristic rotational temperature, which again can be given in terms of beta, which again is a temperature component, HC, which helps correct for units, and beta, which is our rotational constant. So again, this one can be spectroscopically determined, and we'll go ahead and look at how to determine that more next semester. However, one of the things we can then make use of is take this partition function and put it into our expression. So since we have -1 over kr, -1 over the partition coefficient, all of these variables essentially pop up into the numerator. And then all I'm left with is the derivative of 1 over, again, my beta times the rotational constant. Now, from here, what we can essentially make use of is that all of the constants, hc and the rotational constant, come out front, and then congratulations, they cancel out with our variables already there. So all I'm left with is negative beta d beta derivative of 1 over beta with respect to beta. So this derivative of 1 over beta just becomes negative over beta squared. So negative over beta squared times negative beta becomes 1 over beta, which is the same as kT. So what we find is that the rotational energy for a linear molecule ends up just being kT. So for an individual molecule, that's kT rotational energy, or for a mole, this would become RT. If you repeat this for a nonlinear molecule, it becomes 3/2 kT. This shouldn't be too surprising, as you get an extra rotational degree of freedom as you go from 2 rotations to 3. And by doing this, we get an extra 1/2 kT worth of energy. So this is often described that an ideal gas has 1/2 kT of rotational energy for each rotational, and it also has 1/2 kT of energy for each translational mode that a molecule possesses. Because again, 3 translations, 3/2 kT energy. 2 rotations, 2/2 kT of rotational energy. 3 rotations, 3/2 kT of rotational energy. So I can use this to actually derive the total energy of an ideal gas. If it's monatomic, it has 3/2 kT of energy. Diatomic, 5/2, because it only has it's linear and only has those 2 rotations. If I'm a nonlinear molecule, I have 3 kT, 3/2 from translations, 3/2 from rotations. This was exactly the behavior that drove our description of the thermodynamic properties of simple systems. Because remember, once we had the energy, which is going to be related to the internal energy as we see later, we're then able to describe all the other behavior of a system. So this is one of the reasons why the partition function is so important. As I change the partition function, I will change the energy available. And this will let me expand into different temperature regimes as well. However, you may notice that the energies we got for an ideal gas ignored the contribution of our last partner, and that's our vibrational mode. So we previously described our vibrational partition function in terms of 1 over 1 minus the exponential of, again, beta, which is our temperature dependent term, Hc, which is essentially there for units, and our vibrational frequency. So again, this is the term that often comes from infrared spectroscopy. So we can then insert this expression into our equation for deriving energy. So 1 over our partition function, derivative of the partition function with respect to beta. So again, as before, the denominator moves to the numerator out front. I'm taking the derivative with respect to beta, and then my partition function inside. However, the derivatives here become a little bit messier. So this time I actually have to hard apply the derivatives to an expression with addition of an exponential in the denominator. So with a little bit of calculus magic, we get essentially an expression, a little bit more of a complicated expression. Where here I've got multiple variates that come in here. We'll notice that we have 1 over the partition function out front, and essentially the partition function squared here. So we can also treat the energy of the system as Hc times the rotational constant, or times the vibrational constant, times the exponential, with, again, based on the probability of my system, times the vibrational partition function. So unfortunately, our expression for our average energy is a little bit messy. However, it is actually possible to simplify the system a little bit by multiplying everybody by e to the beta Hc nu, which helps simplify the dividing everybody by e to the beta Hc, which helps simplify the system down a little bit more, removing our system down to one simple exponential term. So again, not exactly the prettiest expression for an exponential system, but it is fairly useful. So one of the things that's actually really kind of important when trying to examine the behavior of the vibrational energy is that it tends to actually land in two important camps. So it's got this kind of low temperature behavior from which you actually have to use our vibrational energy expression, but it also has more or less a high temperature region where we're going to see a linear behavior of the mean energy with respect to temperature. But again, so what we're going to be seeing is that the behavior of the system is really going to be dominated, as we've seen before, based on the vibrational energy and the temperature. Under low temperatures, it's mostly dominated by this vibrational energy term in a linear region, which quickly gives way to this more rapid increase. However, one of the things that's worth noting is that at high temperatures, it will essentially give me an energy of kT. However, it's very important to note that for all practical purposes, we rarely reach a high temperature regime with respect to our characteristic vibrational frequency. So in practice, what you actually need to do is determine the vibrational constants of each of the characteristic vibrations and use that to determine the average energy for each vibration. So this is a little bit annoying, but it is actually very important when you're, say, trying to determine the energy of a molecule using a quantum mechanical software. So this is what's going behind Gaussian when you do a vibrational calculation. It has to go ahead and turn each of those rotations, translations, and vibrations into energies, which it can then go ahead and turn into internal energies, enthalpies, entropies. However, before we go ahead and examine how we can convert energies into internal energy, entropy, and free energy, we first have to figure out how we go from molecular energies to what's called an ensemble energy. So describing more than the behavior, the average behavior of one molecule. So next time, we're going to go ahead and talk about how to treat a statistical ensemble. Until then, take care.